Hello, this is Gary Millett again, and this is topic number 4 about sensors. This is part 3 of the 3 sensor presentations, and let's get going. So, what we like to talk about here are other MEMS applications. MEMS have made a great impact on the sensor technology world. So MEMS and now NEMS devices, which are nano electromechanical systems devices, are really improving sensor technology. Certainly the airbag in one's car is controlled by a MEMS-based accelerometer and could someday potentially save your life. Just in the medical, industrial, consumer, and automotive fields, the potential uses of MEMS and NEMS as the key component in a new sensor seem limitless at this point. Combined with modern networking/wireless networking technology, application areas also appear limitless. So, show you some figures here, some examples of MEMS applications. This particular figure shows a MEMS-based gyroscope. And of course, MEMS are, again, built on silicon chips. If you look at that diagram, you'll see that the scale there's a bright white bar, and that indicates that's 100 micrometers in length. So the same type of technology we use to make integrated circuits, we've carried over into the MEMS world. There are many applications for these type of devices in the automotive world and other transportation or motion control situations. Again, a MEMS-based gyroscope. This picture shows MEMS-based cantilevers, which can be used to detect various chemicals. So you see some reference cantilevers, then you see other cantilevers there. And what happens, we'll show later on, that using various types of chemicals, you can detect materials using these cantilevers. So an example of this type of operation will be presented later. So here's a NEMS application. This figure illustrates a NEMS-based sensor that can detect certain types of gas. You see the dimensions there, 500 nanometers. So as shown in the inset, the output signal frequency of this sensor changes when there's a certain type of gas present. So you notice that on the diagram it shows gas molecules going into the device. They would cross over these NEMS structures and come out the other end. The out arrow is shown there. And notice the inset shows frequency with time, and no gas exposure is a certain frequency. With gas exposure, the frequency changes drastically, and then back to no gas exposure, goes back to what it was. It's the ambient condition. Of course, frequency can be detected fairly easily, and that's how we would take and use this sensor to change a frequency to indicate to us that we have the gas that we're trying to detect. Here's another NEMS sensor. This picture shows a NEMS-based pressure sensor with details of the locations of graphene membranes. They exhibit a piezo-resistive effect in the picture inset. So that's blown up a little bit. You see 50 micrometers in the inset, and you see R1, R2, R3, R4, and R5. So these graphene membranes are affected, and this particular sensor responds to a change in pressure with a change in resistance. So there's new emerging sensor technologies in many different fields. As mentioned numerous times already, MEMS technologies revolutionize sensor technology for some legacy application areas, as previous slides have shown. A fairly good YouTube video about MEMS is located here in this link. I think it's fairly short. And now we'll switch our attention to some other newly emerging sensor application areas. Most of these new application areas involve the use of chemical, biological, fiber optic, optical, and photonic sensors. So what's happened? Moore's law has successfully predicted the path for microelectronic size reduction for a long time. And semiconductor devices have behaved behave fairly well as they have been shrinking down in size over the decades. However, scaling issues affect chemical and biological sensors. By this we mean that what works on a large or macro scale does not necessarily mean that it will work on a small, that is micro or nano scale. This fact is especially true as we go from microscale to nanoscale sensors. So nature's solution to this scaling problem is to package the sensor molecules, that is the proteins and nucleic acids, within the confines of a cell featuring a fine-tuned water balancing system. For man-made sensors, the smallest wet sensors must similarly be embedded in a fluidic circuit to provide an environment in which the sensor can survive. Much of today's biosensor research is presently aimed at the achievement of the proper environment for these sensors. So we have a little picture here, his little bunny nose. This tends to bode the following. Future sensors will most likely be built from genetically engineered bacteria, proteins, peptides, and designer nucleic acid. Also, sensor array systems appear to provide an attractive means to achieve speed and efficiency. Now again, here's a little picture of a bunny's nose. You might consider that a rabbit has 50 million olfactory or nose receptors that are connected with neurons that communicate three-dimensionally through ion pulses that travel at 200 miles per hour. That's just a bunny's nose. So there's been a push to come up with an electronic nose. The government's been attempting to build an electronic nose for some time now. So this is a JPL electronic nose or e-nose, little blurb. And as it says here, it's from NASA. The JPL e-nose provides rapid early identification and quantification of target chemical species. An electronic nose is an array of semi-selective chemical sensors. The JPL e-nose is 32 sensors which change electrical resistance when environmental composition changes. The sensing array responds in fingerprint patterns to a broad suite of target analytes. Fingerprints are deconvoluted for ID and quantification. Targets include leaks or spills of selected components, mercury, sulfur dioxide, and possibly heating insulation, which signals electrical fires. The JPL e-nose can be used to monitor cleanup processes also. So they've been working on this, and I think this is about their third generation. And again, each generation's gotten smaller and smarter. So let's take a look at chemical sensors. There are four broad categories of chemical sensors. There are chemomechanical or mass-sensitive sensors. That is, mass changes upon absorption of the desired chemical. There are thermal sensors. Temperature changes through chemical interactions. There are optical sensors, changes in light intensity by absorption. And there's electrochemical sensors, changes of potential or resistance through charge transfer. Four broad categories of chemical sensors. So, chemomechanical sensors are the simplest type of chemical sensor. These sensors work by responding to the mass of species accumulating on a sensing layer, oftentimes a microcantilever system. Refer back to slide number 4 that we just saw. So it turns out that the cantilever system, what happens is we accumulate mass on them. Sometimes what happens, we aim a laser beam at the cantilever, and the angle it's at, due to the change in mass, can be detected. Other sensing techniques employed by these types of sensors are to observe the changes in a variety of mechanical properties of solid or fluid media in contact with the sensing surface. In many cases, changes in the resonant frequency of these chemomechanical sensors is used to provide the sensing function. Piezoresistors may be embedded in the cantilever structure, or optical detection might be employed through the use of focused laser light. I just mentioned that. The angle of reflection changes with the accumulation of species on the cantilever. Typical applications would be detection of organic volatiles or humidity in the gas phase. Thermochemical sensors measure the amount of, I won't be able to say this, enthalpy change produced by the chemical to be detected, and from this measurement determine either the presence or the concentration of sensed chemical. Presently, there are two basic types of these chemical sensors, catalytic or thermoelectric. Typical present-day implementations of these type of sensors are shown in the next several slides. So here's some chemical sensor examples. These figures show catalytic thermal chemical gas sensors. The right-hand diagram shows the sensor structure, while the left-hand diagram shows a typical packaged device. On these, if a combustible gas flows over the measurement resistor, which is typically platinum, it will change resistance compared to the reference resistor. An electronic circuit can sense this. You might notice the packaged device on the left-hand side has like a metal screen over it, which allows a combustible gas to flow over the device inside of that structure. These figures show thermoelectric chemical gas sensors. The right-hand diagram shows the sensor structure, while the left-hand diagram shows the typical unpackaged device. If a combustible gas flows over the thin film platinum catalyst, it will heat up and cause the thermoelectric material to produce a voltage which can be sensed. So you can see a substrate on the right-hand side with a thin film platinum catalyst and a thick film thermoelectric material. Notice the graph down below. The temperature appears to be the red dotted figure, and the voltage output appears to be the blue line. So as the temperature goes up, it turns out that the voltage will go up. There are optical chemical sensors. The basic characteristic property of electromagnetic waves, such as amplitude, frequency, phase, and or state of polarization, can be used to advantage for these types of sensors. A Mach-Zehnder interferometer, MZI, can be used as a biosensor to detect various biomolecule interactions. So what happens here is a beam of light is split onto two different paths. One beam interacts with an analyte in the sensing arm, while the other beam interacts with the reference material. So here's a picture of these optical chemical sensors, and on the bottom left, this shows a Mach-Zehnder interferometer, two paths for the beam of light. Typically that will be some type of light guide. After passing through the sensing arm and the reference arm, the light is recombined and changes to the light beam are sensed. This MZI can detect various biomolecule interactions. This figure shows a plot of DNA matches at a concentration of 10 parts per million. So on the right-hand side, you see the graph where things are complementary versus non-complementary. And again, we might even call this a lab on a chip type of structure. There are electrochemical sensors. They are the largest and oldest group of chemical sensors. These sensors make use of electrochemical or charge transfer reactions. So an electrochemical sensor is always composed of at least two electrodes with two electrical connections, one through the probe sample and the other via transducer and measuring equipment. The charge transport in the sample can be ionic, electronic, or mixed, while that in the transducer branch is always electronic. So it gets a little more detailed here. Two basic classifications of these sensors. There's a volt-amperemetric. Sensors are based on the measurement of the current voltage relationship. Potentiometric sensors are based on the measurement of a potential at an electrode with no current flowing. Often these sensors are classified by the underlying electronic components. Chemoresistors, chemocapacitors, or MEMS capacitor sensor, and chemotransistors. So we'll have a couple of pictures of these in a little while, but before that, let's take a look further. Chemoresistors sensors rely on changes in the electrical conductivity of a film or bulk material upon interaction with an analyte. Typical applications: detection of inorganic gases such as hydrogen, oxygen, nitrogen, oxide, or carbon monoxide, for instance. Chemocapacitor sensors rely on the change in dielectric properties of a sensing material upon analyte exposure. Chemotransistor sensors are based on changes in the operation of a field effect transistor, or FET. These chemotransistor devices are known as ion selective FETs, or ISFETs. The gate metal electrode of the FET is replaced by electrolyte solution, which is contacted by the reference electrode. The gate oxide is directly exposed to an aqueous electrolyte solution. They're often used for pH meters. So here's a picture, and you see a substrate. So the field effect transistor is shown there, and as I pointed out, these figures are presented here for the more electronically inclined readers. Top left, chemoresistor sensor. Top right, a MEMS chemical or capacitive sensor. Bottom is a ISFET, ion selective FET based sensor. So what happens if you take a look at the MOSFET and the ISFET down the bottom left, you see what happens is you take and you put a solution on top of the material 2, which is gate oxide, and you have a reference, and it turns out that the characteristics of that device will change, and you can measure that. Biosensors. There are many different types of biosensor technologies. One such technology uses acoustic waves to sense different molecules. In this system, an acoustic wave is passed through a sample, and the changes to the acoustic wave's characteristics are measured, processed, and analyzed. Optical biosensors are also popular in this application area. Typically, fiber optic or FO cables are part of this technology. So here's an acoustic wave biosensor example. This figure illustrates a single-channel acoustic wave biosensor. An acoustic wave signal is transmitted through a substrate that has cross-linker and antibody material layers on it. So if you take a look down below, it shows a piezoelectric substrate, an input transducer, and an output transducer. And the biological layer, there's protein A, a cross-linker it's called, which is put between the output and input transducers. There's an antibody layer, and it turns out you see a specific target antigen. There's a certain color there, and the green is a non-specific target. So it turns out the output signal waveform will be altered by the attachment of the target antigens to the cross-linker antibody layers. This physical occurrence can be sensed electronically. This diagram shows acoustic biosensor signal processing. And so there's a substance input, X channel detector with biolayer X, Y channel detector with biolayer Y. It's a 2-channel biosensor detection system. And it turns out that X channel output and Y channel output are different. And we can use that to our advantage. Part B shows a N-channel biosensor detection system. So acoustic biosensors is a little more complex in their operation, sometimes needing extensive signal processing to provide usable results. The figure depicts the mathematical modeling / operation of array acoustic wave biosensors. These type of sensors have multiple channels with N different biolayers. The resulting output signals from the N individual channels are shown on the right-hand side of the figure. So, what do we do with this? Well, for this example, signal processing allows the different channel signals to be correlated to a particular type of molecule. Note the grouping correlation of the 3 red dots near the y-axis shown in the figure below. So you do some signal processing, and what happens is after the signal processing, we have clusters of dots which pertain to different types of molecules. So signal processing is able to distinguish between different types of antigens or molecules bound to the antibodies as shown in figure C by the different colored groupings, groupings A through E there. Figure B shows a signal constellation much like that found in an 8-QAM communication system. The biosensor signal processing for this example is much like QAM signal detection and yields the result shown in figure C. So if you take a look at figure C, you see we have these different colors which indicate different types of molecules. And this figure shows the molecular structure of 4 different substances, several of which are dangerous explosives. So you see RDX, which is C4 explosive, ammonium nitrate, TNT, and musk oil. Using biosensors, the presence or absence of these chemicals is able to be detected fairly accurately, as shown on the next slide. So Again, through the use of array acoustic wave biosensor and complex signal processing, it's possible to detect certain substances, explosives in this case, fairly accurately as shown here. So again, vapor phase explosive detection, and you see the correlation, the measurement of correlation. Some of the blocks, like the blue blocks, are RDX or C4. Ammonium nitrate are the orange circles, it looks like. The C4 explosive is the, looks like dark blue rectangles. TNT are the greens, and the musk oil are the yellow dots. So it turns out, again, an acoustic wave biosensor with many channels allows one to take and detect chemicals or molecules of certain types. A surface acoustic wave biosensor shown by the top right figure, and a carbon nanotube FET biosensor is shown here on the left, with the associated electronics used to digitize the sensed parameter. So what happens is, if you take a look in the right-hand diagram, we have, again, an input transducer, an output transducer. We have some reference material, and then we have a material we're trying to take and decipher what it is. So a lot of different types of biosensors that are quite complex, but micro-miniaturized, as you can see. Here's back to the cantilever. This provides more details about MEMS cantilever sensors, which are B and C. And the target molecules bind to the probe molecules, causing the MEMS cantilever to bend or deform, as shown in A. So the target molecules are the ones floating above the cantilever. The probe molecule is a layer of gold and silicon nitrate microcantilever, and it turns out the targets bind to the probe molecules, and as they do that, it bends the cantilever. This can be detected through the use of a laser beam reflected off of the cantilever surface, as shown by figure D. So I mentioned before, you take and you shine a laser, and what happens is there's a frequency shift, parts per million from resonance, and you can use that to measure what's going on with these devices. Rather complicated stuff. Fiber optic biosensors. In this case, somewhat like the acoustic wave biosensor, a fiber optic cable is coated with capture antibodies. You'll see this on the next slide. When a sample is applied to the fiber optic cable, the desired antigens will be captured, that is, if they were present. If at this point a laser beam is sent through the fiber optic cable, the detection antibodies that have bound to antigens will fluoresce. The amount of fluorescence is what is detected by the sensor. So here you see this figure. It depicts the operation of fiber optic based biosensor. So the top one, you see a lens there, it looks like, with the fiber optic cable. There are capture antibodies. Then the second one down, there's a sample applied. The antigen binds to the capture antibodies, which are the, I guess, long rectangular yellow things. Other cells and debris are washed away. And then what happens, the laser is turned on, and detection antibody binds to the antigen and fluoresces when laser is turned on. So you see those things oscillating, the detection antibodies. And the amount of fluorescence is proportional to the concentration of the desired antigen. The frequency of fluorescence is characteristic of the particular antigen material. Again, fiber optic cables and laser beams being used to take and detect various materials. Here's another fiber optic biosensor example. In this case, the figure depicts a biodetection sensor using a single mode fiber optic cable. The end of the cable is gold-plated and placed in an analyte medium. A single mode light signal propagates down the fiber optic cable until it gets converted to a cladding mode signal by the long period grating structure, that's called the LPG. The cladding mode signal interacts with the analyte, that is, some of the energy is outside of the cable, and this cladding mode signal interacts with the analyte and is reflected by the gold layer. The reflected signal propagates back down the fiber optic cable It's converted back to a single mode signal by the LPG towards the detector where it's sensed and measured. So we send a signal in there, and it turns out that in the inlet medium, the sensing area will get changes to that signal, and what happens is we can detect it as it gets bounced back. Again, a lot of the details are missing here, to say the least. Photonics at MIT. It turns out we at STIC are working with MIT on their photonics sensor project. Each semester we take STIC optics and photonics students to MIT to interact with their project. If you want to see a YouTube video, the link is below the picture below. It's an interesting YouTube video about what they're doing in the world of photonics sensors. What about microfluidics, MEMS, and biosensors? Well, before leaving the topic of biosensors, we need to introduce the concept of MEMS and microfluidics. Microfluidics is the ability to make networks of interconnecting channels on a chip or substrate. Precise liquid pumping and handling may be accomplished using applied pressure or centrifugal force. Microfluidics facilitates the implementation of many biosensors and enables the concept of a lab on a chip. Here's a link here for a YouTube video that you should take a look at about this type of technology. So here's a picture of microfluidic device examples. These two pictures show microfluidics devices that are used to control the flow of minute amounts of fluid for further processing. And again, this is typically the type of technology used to make a lab on a chip. I don't have a picture here, but if you do a search on Google of lab on a chip, you'll see a lot of architectures of how those things look. And again, a key component is the microfluidic devices that I have pictures of here. Other applications of fiber optic and photonic sensors. Well, this is a very large field. There are so many applications of lasers, fiber optic cable, and the photonic sensors in the areas other than biosensors that's impossible to cover them all. Imaging and spectroscopy have always been important optical applications, but today many new and novel applications have been proposed or developed for use. A future technology that's just started to come out of the laboratory is a photonic IC, or PIC, as we call them. A few of these newer applications will be introduced here. So probably the most common type of fiber optic sensor, fiber optic cables with Bragg gratings have narrow band reflectivities with center wavelength changes with the sensor's temperature or strain on the cable. So it is possible to string a series of these gratings with different center frequencies along a single fiber optic cable. Thus, the fiber could provide a large number of outputs, that is, sensor readings, that are position dependent. And again, there's a YouTube video here you might take a look at this type of technology. So let's take a look at this fiber optic Bragg grating theory. So as shown by this diagram, a Bragg grating causes a reflection of a particular band of light frequencies as they propagate down a fiber optic cable. So you see the incident spectrum up above, and it's all visible light. Goes down the fiber optic cable that's got Bragg gratings, and what happens is what's transmitted is there's a notch, and it looks like the notch is basically between the green and yellow frequencies or wavelengths, and lo and behold, a reflected spectrum is the notched out light, and so what you get coming back is on the bottom left there from that fiber Bragg grating cable. Now, what happens is if I have an unstrained fiber Bragg grating, well, what we saw in the prior slide will be what will happen. A strained fiber optic cable with Bragg grating causes shifting or reflection of a particular band of light frequencies as they propagate down the fiber optic cable. This shift can be measured by electronics. So the strained cable down below, notice what's happened. There's a different wavelength of that peak, and again, we can measure that with electronics. So you might put these things in buildings, in concrete forms, and so forth to see whether things are stretched. There's been a lot of research of putting these things into highways to take a look at what occurs to a highway. So during new construction, it is becoming more commonplace for fiber optic sensors to be embedded in a highway, bridge, wall of a building, etc., to monitor the health of the structure. Using off-the-shelf components, Typically used for telecom applications, one can interrogate one fiber sensor at a time and check for structural aging, or alternatively, alarms can be set up to monitor for structural failures or to notify a central monitoring point of immediate problems. And again, here's a YouTube video about this type of technology. So here's this picture comes from the U.S. Department of Transportation website. Shows, although not very clearly, the installation of a fiber optic sensor in the interior of the rebar of a highway construction project. I've looked at this numerous times. It's very difficult to see where the fiber optic cable is there. But again, it came off of the Department of Transportation website, so we assume it is an accurate picture. Here's a different picture. Excuse me. And this one is an instrumented reinforcing cage of a large board pile with fiber optic sensor cable, that's the blue cable, and conventional strain gauges, that's the red cable. And again, there's a YouTube video there, but you should note this video is over an hour long, so I don't know if you want to really take a look at that unless you really get into this. So, smart sensors. Today's smart sensors will include a microcontroller, memory, and an interface for communications. These subsystems serve various purposes: to be able to control the sensor's operation and function, to provide measurement correction over the sensor's range, and to provide a digital interface to the control system to send and receive data and program updates. The IEEE has a standard. It's number 1451.x, 1451.x for smart sensors and actuators. The transducer electronic data sheet, or TEDS concept, is key to the standard. Under microcontroller direction, the smart sensor can be programmed to make measurements at certain time intervals. We note the typical microcontroller has several programmable timers on board, which can be used to trigger events. The number of data bits representing the sensor sample may be changed or altered. Error correction can be used to compensate for nonlinear characteristics of the sensor. The entire function of the sensor can be changed by downloading a new program. So smart sensor technology is the biggest thing right now. So let's do a summary of sensor technology. MEMS technology, our ability to put micro electromechanical systems in an IC chip, combined with available electronic subsystems on the same IC chip, has revolutionized sensor technology. And again, there's a short little video about this from YouTube. Furthermore, sensor technology is spread into the fields once devoid of sensing technology, except for, say, vital signs. And by that, we mean that the medical field is ripe for this type of new technology. And I think that's the last slide for this one. Nope, one more. Unique sensors for use in the medical field and civil engineering fields have recently changed how we do business in these areas. The ability to use wireless technologies to remotely gather data has further changed how we look at what we can and cannot do. As we go forward, sensing will become more and more ubiquitous and will provide richer and richer data sets to be processed by us and information abstracted from that data. I think that's the last slide.